let's find our way back. It is fully 10:30, so we're going to get started with our next presentation. So please find your way back to your seats. Thank you for those online for bearing with us while we start just a minute or so late here. Our next presentation is by Ted Pine with Nitrexo Limited, coming from Ireland. And the title of his talk is From Manual to Automated, Optimizing Spacecraft Thermal Engineering Processes with AI. Ted Pine is a thermal engineer at Nitrexo. He brings a multifaceted aerospace background spanning aeronautics, spacecraft operations, and design. Leveraging his expertise, he's forged a niche in implementing innovative AI and machine learning strategies to address complex challenges in aerospace engineering. His current work focuses on improving traditional spacecraft thermal engineering processes, demonstrating the transformative potential of automation in the field. Today, Ted is excited to share his insights on optimizing spacecraft thermal engineering processes with AI. And he'll be joined during the Q&A. So he is presenting to us remotely from Europe. He'll be joined during the Q&A with the CEO of Nitrexo, named Yannick Melameka. So let's give it over to Ted, who'll be joining by video, and then we'll see him during Q&A after.
Hello everyone, my name is Ted Pine and I'm a thermal engineer with Nitrexo. I'm excited to share with you, the Space Thermal Control Workshop 2023 attendees, Nitrexo's continuing work on optimizing spacecraft thermal engineering processes with artificial intelligence. Today, we will explore the exciting prospect of AI-driven automation in spacecraft thermal engineering. As it stands today, the spacecraft thermal engineer plays a critical role in designing and analyzing thermal control systems to ensure spacecraft can survive and operate in its mission environments. As spacecraft systems continue to evolve, becoming more complex and sophisticated, there is a growing demand for high-performance systems, miniaturization, and multifunctional components. Its increasing complexity highlights the importance of accurate and reliable thermal modeling to ensure mission success. However, traditional thermal modeling processes often face challenges such as time-consuming manual efforts for model construction, modification, and validation, as well as difficulties in adapting to design changes and evolving mission parameters. Moreover, accurately modeling thermal behavior in extreme environments and for complex systems can be a very difficult task. Recent advances in AI and machine learning are now offering new opportunities for automating and optimizing thermal modeling processes. These advancements have the potential to reduce manual intervention, increase efficiency, and enable engineers to focus on high-level problem solving. Throughout this presentation, we will discuss real-world examples and best practices for integrating automated technologies into thermal engineering workflows. So without further ado, let's dive into the transformative world of AI-powered spacecraft thermal engineering. Before jumping in, I think it's useful to take a brief journey through the history of spacecraft thermal engineering tools, highlighting the key developments that have shaped the field today. In the pre-20th century, the foundations of thermal engineering were laid with the development of calculus by Newton and Leibniz in the 1600s, followed by the establishment of thermodynamics by Maxwell, Clausius, and Kelvin in the 1800s. The field continued to progress with the emergence of statistical mechanics, pioneered by Boltzmann, Gibbs, and Planck. Moving into the mid-20th century, numerical methods for aerospace vehicles were introduced and quickly adopted by NASA for the design and analysis of spacecraft. These early tools laid the groundwork for the evolution of spacecraft thermal engineering. In the late 20th century, we see the proliferation of computer-aided design and the advent of high-performance computing, allowing for more complex simulations, propelling the field forward. As we entered the early 21st century, modern thermal analysis tools such as ANSYS, Thermal Desktop, and ECETAN emerged, providing advanced capabilities and enhanced accuracy in thermal modeling. Now, in the mid-21st century, we are witnessing the integration of modern tools with digital assistants, powered by artificial intelligence and machine learning. This transformative development is paving the way for a new era of efficient, automated, and intelligent spacecraft thermal engineering. Throughout this presentation, we will explore how these advancements are shaping the future of the field and how engineers can leverage these cutting-edge technologies to optimize their workflows. It is well understood that, broadly speaking, spacecraft missions are growing in complexity. NASA's JPL has identified 4 primary categories of complexity factors. First being project technical design complexity. This refers to the inherent challenges and intricacies involved with designing cutting-edge spacecraft systems, components, and instruments. Number 2 is project programmatic complexity. This encompasses the management and coordination aspects of a space mission, including budgeting, scheduling, and risk management. Third is the lack of resiliency. This factor highlights the potential vulnerability of a mission to unforeseen issues or failures, making it crucial to develop robust and adaptable systems. And lastly, number 4 is new design challenges. As spacecraft missions strive to achieve more ambitious objectives, engineers are often confronted with unprecedented design challenges that push the boundaries of technology. As mission complexity increases, so too does cost. And to mitigate these costs, there is a need for more efficient engineering processes. By streamlining and optimizing spacecraft thermal engineering workflows, we can achieve lower costs and ultimately enable more ambitious and innovative space missions. Traditional thermal modeling processes have several limitations. First being time-consuming manual efforts. Engineers must spend a significant amount of time creating, modifying, and validating thermal models to ensure accuracy and reliability. Number 2, difficulty handling complex spacecraft systems. As spacecraft designs become more intricate and sophisticated, traditional thermal modeling methods can struggle to keep up. Limited adaptability. Traditional approaches often have a difficulty adapting to design changes or new requirements that arise during the development process. When constructing a thermal model, engineers must perform several manual tasks, such as defining geometry, materials, and properties of components, setting up boundary conditions, heat transfer coefficients, and radiation properties, balancing trade-offs between model complexity and computational efficiency, establishing thermal couplings and interfaces between components, revising models to incorporate new design changes or responding to a new mission requirement, correlating thermal model predictions with test results. So it's safe to say that whilst modern tools have allowed the thermal engineer to better design, predict, and understand their thermal control system, there still exists many time-consuming and laborious non-value added tasks in the workflow. Thus, the need to reduce that, reduce the time and cost spent here is significant. Recent developments in the AI and machine learning fields offer the potential to optimize our spacecraft thermal engineering processes. In the area of geometry construction, we can utilize convolutional neural networks for efficient shape recognition and generation in thermal models. For subsystem modeling, such as multi-layer insulation and heat pipes, we can employ support vector machines for accurate prediction of insulation properties, or leverage physics-informed neural networks for enhanced understanding of heat transfer processes. Dimensionality reduction is another key aspect. By implementing autoencoders or other unsupervised learning techniques, we can generate comprehensive thermal models from simplified versions, streamlining the overall modeling process. Model tuning and optimization can be achieved by harnessing genetic algorithms, which can effectively correlate various parameters in thermal models. Lastly, knowledge transfer and communication play a vital role in any engineering project. Advanced language models can be employed for seamless education, knowledge transfer, and even automated report generation within an engineering team. Now let's discuss the promising outcomes of integrating AI machine learning technologies into spacecraft thermal engineering processes. Time savings is a massive one. So streamlining processes and automation leads to reduced time spent on manual tasks and model construction. Rapid design exploration. The time saved could be, in some cases, better utilized to explore design space and optimize spacecraft thermal performance even further. Improving knowledge transfer. Advanced language models facilitate the seamless communication education, and documentation within the engineering team, and focusing on high-level tasks. So AI-driven automation enables engineers to concentrate on strategic problem solving and decision making, ultimately increasing the productivity and innovation. By leveraging AI and machine learning technologies, we can really revolutionize the way spacecraft thermal engineering and thermal modeling processes are carried out, resulting in more efficient, accurate, and robust thermal control systems for future space missions. Take a look at one of the thermal engineering processes we are building automation tools for at Nitrexo, geometry mathematical model instruction through a real-world example. The Copernicus CO2M mission plays a critical role in monitoring global CO2 emissions and contributes significantly to climate change mitigation efforts. The mission's success depends on the reliable acquisition and transmission of crucial data related to CO2 emissions. The Ka-band downlink antenna system is a key component of this mission, and maintaining precise thermal control is essential to ensure reliable data transmission. Any deviation in the thermal performance of the antenna system could lead to a reduction in signal quality or even loss of data, ultimately compromising mission objectives. With a complex instrument such as this, the creation of a GMM from the original step file is time-consuming and laborious. Furthermore, design changes may require the process to be repeated by a thermal engineer many times over. With parametric deletion, rules-based methods, as well as machine learning algorithms, Nitrexo is developing approaches to automate this process that we hope to share with the space community in the future. Let's now discuss the crucial steps for integrating automated technologies into thermal engineering workflows. The goal is to harness the power of AI and machine learning to enhance our capabilities, improve efficiency, and foster innovation. So let's really go through here 7 key steps for that. So the first, gradual integration of automation. So we begin by automating repetitive and time-consuming tasks and expand automation capabilities as team members become increasingly familiar with AI technology. Our second step, developing a multidisciplinary approach. Fostering collaboration among thermal engineers, AI experts, and other stakeholders is key. And we need to do this by encouraging cross-functional systems and teams and continuous learning to keep up with technology advancements. Ensuring data quality and availability. Collecting and maintaining high-quality data for training and validating AI models. Establishing standard data formats and protocols to facilitate data sharing and collaboration. Number 4, implementing feedback loops. Continuously evaluating model performance against test data or experimental results. Adjusting and refining AI models based on feedback to improve accuracy and reliability over time, whilst encouraging open communication between team members to identify areas for improvement. Balancing automation with human expertise. It's another crucial one. Recognizing the value of human judgment and experience in thermal modeling. Integrating AI-driven automation as a tool to enhance rather than replace human expertise. Number 6, establishing validation and verification protocols. Develop rigorous procedures to validate AI-generated models against established standards and benchmarks, ensuring the reliability and safety of AI-driven thermal models, particularly for safety-critical systems. And lastly then, in number 7 here, fostering a culture of innovation. Encourage experimentation with new AI-driven techniques and methodologies. Support continuous improvement and optimization of thermal engineering workflows, emphasizing the importance of adaptability and resilience in the face of rapidly evolving technology landscapes. By following these steps, we can successfully integrate AI and machine learning into our thermal engineering workflows, unlocking the full potential of these cutting-edge technologies and driving innovation within our industry. I thank you for taking the time to listen to our presentation and really encourage that if you would like to collaborate with us, you can do so by reaching out at info@nitrexo.com. Other than that, thank you again very much for listening and enjoy the rest of the conference.
All right, thanks very much, Ted and Nitrexo for presenting. At this time, we should have Ted and Yannick online. There they are.
Yes.
Great, so we will take questions either from the floor or from online. Jake, again, Supawit will relay questions through the chat verbally, so those in the room can see them. Those online probably already can see them. So we've got Ted on the left. We've got Yannick on the right. So do we have any questions for either one of them? Can you gentlemen say hello, just to make sure we can hear you?
Hi, everybody.
Hello.
Yeah,
Hello.
Good. Great. We can hear you. Any questions for Ted?
Ki Huan from Boeing. Can you hear me?
Yes, we can hear you.
Yes, we can hear you.
Sure. Thanks for the great presentation. I have many questions, but I like to ask one specific question. In the slide where you talked about geometric construction, as you know, a lot of AI is really about preparing data as input. That's where the most of the work for AI comes in. How would you, do you have a specific plan to how to carry out this part?
Sure, I can maybe take that one first of all. So yeah, data scarcity, I think is really the key problem here, and yes, that's something that pretty much any AI machine learning project, regardless of the discipline, more data equals better results, right? But I suppose there's also some mitigations you can have. So of course you need data, but there's certain steps that you can take if you get the most out of the data that you have. So I mean, for our case, utilizing so we mentioned in one of the slides about parametric rules. So there's certain depth for thermal modeling that you do pretty much in every single mission. So if we can develop some rules-based methods first, that helps. Also, you have something called transfer learning. So you can take models that have been, say, pre-trained on a certain data set and utilize the knowledge and do additional training on top of that. So you don't need to start from scratch. But absolutely, in every machine learning AI project, data is a key part of that. And yeah, more data always equals a better result in machine learning.
Thanks, Ted. Also, I want to encourage you, if it's relevant, you can refer to your charts. We'll just have to make sure that you're presenting the charts on the screen there. Next question, we've got Brad Reed.
Hi, my name is Brad Reed. I'm from WR Scientific. The siloing of data is an issue, I think, with AI applications because AI wants to feed on data from multiple sources, yet if you're developing a package for a company, as opposed to some of these applications that are free right now that just take information off the internet, you run at a disadvantage of only working to the data from inside that company because they want to protect their data. They don't want to share, like Lockheed is not going to want to share data with Airbus on its designs for spacecraft. So how do you intend on developing data sources that can be shared throughout the world, but still be siloed within companies to keep their proprietary and their security information safe?
Yeah, so I can take that. So I think the first thing is that I would like to mention is that we are an engineering company, right? So we have our own data, and actually we capitalize our data within the software, right? And so that's one thing. So we do have data, and we can use it. And the way also the way to protect the customer data is, so first of all, the data can remain within a wall, so they can keep the data within a wall, and they can actually feed, let's say, the AI with the data, but in a way that those data remain within their wall. All right. So does the answer to your question?
No. What you end up is, we had discussions on this over the past 2 days within the room about how AI is supposed to pull in data from multiple sources, but how do you reconcile that one company's, let's say you provide an AI package and you provide a company-specific AI package. What are the computing resources that are needed? What are the data resources that are needed? And how, like if Lockheed has a solution, let's say you give Lockheed and Airbus, because I use those two companies as an example. They have the same problem that they're bidding on for a job from NASA. How could you reconcile that with two separate data sets, Airbus's data set and Lockheed's data set, that you would converge on essentially the same solutions to the problem? Because if we're optimizing solutions to the problem, there should only be one solution left at the end of the day that would be optimized for a specific mission requirement. So I'm still confused in how AI is going to help by siloing data sources, because companies are proprietary entities, and still coming up with optimized solutions that would be the best solution, or something that humans wouldn't necessarily think of. Because you've got a bunch of humans in this room who actually do this work, and they think they have the best solutions. And what we're talking about doing with AI is finding solutions that the humans wouldn't normally come to, wouldn't necessarily think of in their own silos. So how do you reconcile not having all of a global set of data, but still trying to put together a set of software? And by the way, I'm a software engineer from 35 years ago. Putting together a set of software that addresses the thermal problems universally.
Yeah, I think I can address maybe some of the things you mentioned there. So in terms of, say, a company-specific package, so even already, right now, we have some, so large language models. A large language model is, ChatGPT is a large language model. There's other large language models out there. There are a couple that are actually space-specific. So I know of a few large language models that are specifically trained on ECSS requirements, as well as a couple of other data sets. So those can be used as a foundational model. And then if a company wants to go and develop an in-house package, say a digital assistant for their workflows, you can utilize the base understanding from something trained on like ECSS requirements or best practices, and then train it also on the company-specific workflows and best practices. So, but that's one way of addressing the company-specific needs. I don't know, Yannick, if you want to add anything further.
Yeah, well, also the thing I would like to say is that the task that we are focusing on today, that we are digitalizing and automating, the standard task. So what I mean by standard task is that pretty much every company has to go through the same single task every time, so like building the geometry and so on. All right, and so I mean, if you implement a way to actually automate it, using some test data and also some flight data, it's gonna work pretty much for anyone, because this is some kind of standard task. So that's one thing, and the second thing is that we allow the company to actually capitalize their knowledge and remain within the company, so they don't have to share it. It's also a good way for them to actually capitalize their own knowledge So at least, when some newcomers are coming in the companies, they can get access to it straight away, all right? So there is this component where you can actually capitalize your own knowledge, right, within the company.
More questions from the room or online? Yeah, come on up.
Hi, Charles Owens from UC Irvine. I just had a question on the motivation slide. You guys showed complexity versus future growth costs.
Speak up a little, Charles.
Oh, can you hear me now? On the, I think it was one of the first slides, you guys had a chart, complexity versus cost. Do you mind elaborating what complexity means in this case? What gives it a value of 1, 2, et cetera?
Sure. So I really, the purpose of that slide was to really justify that the spacecraft we're developing are growing in complexity. I think we're seeing that throughout the industry. We're seeing new products and services being developed, new environments that we're operating in, and new requirements within those environments. So any tool that allows us to get through the steps that we need to as thermal engineers to a designed, validated, manufactured, operating, thermal control system is of value to any any organization.
Do we have another question from online?
Yep. So how long did it take to create the GMM that was shown in your slides from setting up the AI to training and validating the final model?
1 week.
1 week was the answer.
Yes.
I have another question. So we talked a lot about getting data to train the models, but can you elaborate a little bit on what you're training the models on? For example, how do you go from a CAD to a thermal model? What sort of inputs are being taken from the CAD? For example, maybe we take mass and only keep the high mass components, maybe a mate's identified in the CAD and then a contactor is applied there. Sort of how is the AI extracting information from the CAD to build a thermal model?
Was the question clear?
Yeah. You mean, as the information that we look at, actually, what we do is we look at some, let's say, standard rules when you actually build the geometry, all right? For instance, typically when you build a thermal models, you're going to remove the small features, all of these kind of features, because the area is very small as compared to the surrounding area. And so we establish some rules and we validate these rules with existing data, right? So some test data. And once it is done, then we can actually implement the algorithm. So which is basically every single step that you have to go through to actually create the geometry. And then we are automating the task, So this is what we do right now. So we are actually defining some rules that you need to actually use pretty much in any project when you build the thermal model.
Okay, thanks, Yannick. That's all the time we have for questions. Thanks, Ted and Yannick, for the presentation. It looks like you're still in development, and I know this is just looking at the faces in the room, it's a curious audience. So I encourage you to come back next year, visit some of the other thermal-related space conferences, and you'll have lots of people want to talk to you some more. So thank you.
That's good. All right. Thank you
very much,
Thank you
guys.
very much. Take care. Bye.
All right. Our next presentation is by Doug Bell, now with ANSYS as Cullimore and Ring.